On number 3, we want to find the differential dy. So remember, as we're finding that, we need to first find the derivative. So as we look at this x times 1 minus cosine x, we know we're going to have to use the product rule. So let's think of u as x, which means u prime is 1. And then let's think of v as 1 minus cosine x, which means v prime would be sine x. So then as we combine u prime v plus uv prime from the product rule, we would have 1 times 1 minus cosine x plus x times sine x, which distributing your 1 through, or 1 times anything, is just the same thing. So we would have 1 minus cosine x plus x times sine x. So remember, that is dy dx. So that means the differential dy would be that derivative, the entire quantity. So I'm putting some brackets here. 1 minus cosine x plus sine x times dx. Alright, this next one we have another problem that wants us to use differentials. So here we're looking at the radius of a sphere is measured as 9 centimeters, but they're giving us a possible error of about 0.025 centimeters. So as we're looking at that, that's the error on the radius. So in our case, that's going to be our dr. In part A, they want us to use differentials to approximate the possible propagated error in computing the volume of the sphere. So kind of remember, if we have an error with the radius, that's going to translate to an error in the volume as well. So remember, for a sphere, the volume is 4/3 pi r cubed. So if we find dv, actually, let's just go ahead and find dv dr, the derivative of the volume with respect to the radius first. We could bring our 3 down to the front. That would cancel with the 3 that we have in the 4/3. So that would just give us 4 pi r squared. So that means then dv, the differential of v, is 4 pi r squared dr. So remember, they're telling us r is 9. And then that 0.025 is essentially our dr. So plugging those in, we would have 4 times pi times 9 squared. And that error could be too much or too little, so I'm going to put a plus or minus 0.025 for my dr. So that would give me plus or minus, throw that all in your calculator or whatever you want to do there, 81/10 pi, which would be about plus or minus 25.45, and volume would be measured in cubic units, which was centimeters, so that would be centimeters cubed. As we look at part B, we're doing kind of the same thing, but now we're looking at the surface area of the sphere. So for a sphere, the surface area is given by 4 pi r squared. So again, the first thing we want to do is take the derivative of that surface area with respect to radius. So this time that would give us 8 pi r. So that means for the differential of surface area, we would have 8 pi r dr. So again, that r value is 9 and dr is at 0.025, either plus or minus. So that's going to give me plus or minus 9/5 pi, which a decimal approximation would be about plus or minus 5.65. Surface area would be in centimeters squared. So there are our values for A and B. And then in part C, they want us to approximate the percent errors in parts A and B. So as we're looking at part C, remember our formulas for the percent error. So for volume, I would have dV over V. So formula-wise, that would look like my 4 pi r squared dr over 4/3 pi r cubed. So we could simplify that here. That would leave me with 3 dr over r. So again, remember that the r value is the plus or minus 0.025, and our r value is 9. So that's going to give me about plus or minus 0.00833. So as far as a percent, move my decimal place over a couple spots, that's going to be about 0.833%. All right, so then doing the same thing for surface area, we would have surface area in the bottom. So this would give me formula-wise 8 pi r dr over our 4 pi r squared. So that would simplify then to 2 dr over r. So that would give me, again, plugging in that 0.025, the plus or minus for dr, and 9 for r, about plus or minus 0.0056, or again, moving the decimal spot twice, a 0.56% possible error for surface area. For number 5, we have quite a few indefinite integrals. So if we look at A, remember we can split this up over addition, subtraction, so these are all just power rules. So remember we want to add 1 to our exponent and divide by that same number. So we would have 4x cubed divided by 3 plus x squared divided by 2 plus 3x, and then we always get a plus c at the end for that constant of integration for indefinite integrals. For part B, notice we have division here, and we can break this up because there's just a single term in the denominator. So I would probably just go ahead and rewrite this as x to the 4th over x cubed plus 8 over x cubed to start with. So then as we simplify or rewrite this a little bit, x to the 4th over x cubed would just leave me with x. And that x cubed in the bottom for my second term is the same thing as x to the power of a negative 3. So again, just a couple of power rules. Remember, we add 1 to the exponent and divide by that same number. So that first term would give me x squared over 2. For the next one, notice that we have a negative exponent. So negative 3 plus 1 would give me a negative 2. And then remember we divide by that same number. So I'm going to divide by negative 2 as well. So then rewriting a little bit to clean this up, we would have 8 divided by negative 2, which would give me a negative 4. And then x to the power of negative 2 would be the same thing as x squared, but in the denominator. And then again, that plus c at the end for our constant of integration. All right, so then on part C, again, we can split this up over addition, subtraction. So for the first piece, adding 1 to my exponent dividing by 2 would just leave me with x squared. And then as I'm looking at the antiderivative of a negative sign, that's going to give me a positive cosine. And then that coefficient of 9 is just going to tag along. So we get x squared plus 9 cosine x, and then again the plus c, or constant of integration, at the end. Alright, so then when we get to part D here, this is where we're going to have to use u substitution. So as I'm looking at my u and kind of choosing what I would want to start to try for u, usually we look at the quantity that's being raised to a power, or in this case under a square root, because I can think of that as a power of 1/2. So if I set u to be x cubed plus 3, that means du would be the derivative of this, which would be 3x squared dx. So as we're kind of looking at the pieces we have and the pieces we need, I already have my x squared and my dx, so the only thing I'm missing is 3. So if I multiply by 3 on the inside of my integral, I'm going to multiply by 1/3 on the outside of my integral. So overall, when I translate that then to an integral in terms of u's, I have my 1/3 out to the front, but that 3 along with the x squared and the dx is all just the same thing as du, and in the bottom we would have 1 over the square root of u, which, remember, if we rewrote, would just be u to the power of negative 1/2. So then once we do that substitution, Remember, we're doing substitution to get it to a form that I can integrate. And that's exactly where we're at because I can just use that power rule. So remember, I'm going to add 1 to my exponent. So negative 1/2 plus 1 would give me a positive 1/2. I need to divide by that same value, so a positive 1/2, which remember is the same thing as multiplying by 2. So that would give me really 2/3. And then that u to the 1/2 is, remember, just the same thing as a square root. And u, remember, is x cubed plus 3. So we want to plug back in for our original variable at the end. Okay, so then if we look at part E, we are again going to need to use substitution. So we have a sine cubed x, so that power of 3 tells me I would probably start by letting u be equal to sine x. If I do that, that means du would be equal to cosine x dx. So I can rewrite this entire integral in terms of u's and du's pretty easily. So sine cubed would be the same thing as u cubed, and then that cosine x dx, remember all of that is equivalent to du. So another simple power rule, I'm going to add 1 to my exponent, divide by that same value, and then we always get our plus c, or that constant of integration. Again, the last thing we want to do is just plug back in. You can divide by 4, or think about multiplying by 1/4, that's the same thing. But u, remember, was sine x, so u to the 4th is the same thing as sine to the 4th, and then we have our plus c for our constant of integration. Alright, so then the last one, part F here, we have again some trig functions, and we're going to need to use substitution. So I start with that 1 minus sine theta for u, because we usually at least try using whatever is being raised to a power, and in our case the square root is the same thing as a power of 1/2. If I let u equal this 1 minus sine theta, that means du would be the derivative, so negative cosine theta and then times d theta. So we have almost all of our pieces. I have the cosine theta, I have the d theta. The only thing I'm missing is that negative sign. So if I multiply by a negative on the inside, I would need to balance out by a negative on the outside. So then when I rewrite that, that negative on the outside is going to remain, but the negative cosine theta, d theta, all of that on the inside is just going to be the same thing as du. In the denominator, we have that square root of 1 minus sine theta, which is the same thing as the square root of u. So in terms of powers, that square root of u in the denominator, remember, is the same thing as u to the negative 1/2. So when we use our power rule to find our antiderivative, we're going to add 1 to that exponent, giving me a positive 1/2. We need to divide by that positive 1/2 as well, which is the same thing as multiplying by 2. And then plugging back in for our original variable, remember u is the same thing as 1 minus sine theta, so that square root of u, or u to the 1/2, would be the square root of 1 minus sine theta. And then again, we always get our plus c, or that constant of integration, at the end. On number 6, we're finding the particular solution that satisfies the differential equation. So here they're telling us the derivative, so f prime of x is equal to negative 6x, and then they're giving us an initial condition that f of 1 is equal to negative 2. So remember, if I'm trying to find f of x, what I need to do is find the antiderivative of f prime of x dx. So our f prime of x is what they gave us as a negative 6x. So if I find my antiderivative there, we just need to again add 1 to our exponent, divide by that same number, and then we always get that plus c. So negative 6 divided by 2 would give me a negative 3x squared plus c for f of x. But we want to find the particular solution, so remember that involves actually solving for that constant of integration c. And we are able to do that from the initial condition that they gave us, that f of 1 is equal to negative 2. So that means when x is equal to 1, f of 1 is negative 2, or f of x is negative 2. So looking at that for our equation, we would have negative 2 is equal to negative 3 times 1 squared plus c. Well, 1 squared is just 1, so we have negative 2 is equal to negative 3 plus c. Solving for c means I need to move that negative 3 to the other side, so if I add 3 there, negative 2 plus 3 would give me a positive 1. So I have a positive 1 for c. So that lets me then plug that c value back into my equation for f of x to come up with my particular solution. So instead of just that generic constant of integration, I know for this, my constant of integration should be equal to 1.